in this video, I'm going to be talking about a combinational circuit called a full adder. Okay, so by definition, what is a full adder? By definition, what is a full adder? So a full adder is simply a combinational circuit. It's simply a combinational circuit. A full adder is a combinational circuit that is designed to add three binary digits. So it's a combinational circuit that is designed to add three binary digits. Okay. So why do we have a full adder? We have a half adder and a full adder, right? So a full adder had a drawback. The drawback of a full adder is that a full adder couldn't add when it's doing its calculation. When a full adder, when half adder is doing a calculation, it only adds the bits A and B. It doesn't consider the carry. Okay. So the full adder, okay, this one was developed to overcome the drawback of the half adder. So what is the drawback of the half adder? The drawback of the adder, the full adder is developed to overcome the drawback of the half adder. What is the drawback of the half adder? Okay. So drawback of half adder. The drawback of the half adder is it does not add the remainder. Does not add the remainder. Does not add the remainder or carry in its operations. Okay, so a full adder was developed for this reason, so that it should be able to do what? Able to add the carry or the remainder in its operations. Okay, so it's a combinational circuit that is designed to add the three binary digits, developed to overcome the drawback of the adder. Drawback of the half adder does not add the remainder or the carry in its operations. So the full adder comes now to add the carry in its operations or in calculations. Okay, so meaning this one is more accurate and precise. More accurate and precise than a half adder. Okay. So what do I mean by accurate? Example. Okay, this example might not sound like the real world example, but let me give you this scenario. Let's say we have a building, like this one. Let's say we have a building with about a number of floors, right? So that building looks like that. Let's say that this building has got 30 floors. Then there's an elevator here. Okay, so if you are using, let's say that this elevator requires about 250.8 volts for it to be lifted from the ground to the last floor, to the 30th floor. Okay, so if you use a half adder to implement this type of a technology, what will happen is that the half adder does not count these decimals. It does not put the decimals into account, right? Because these are the remainders. A decimal represents a remainder in a fraction. So it does not put into account the remainders and the decimals in its calculations. So this means that if you're using a half adder to implement this type of a circuit, it means that you can only have access to 250 volts. Meanwhile, for optimum performance or for optimum movement, the elevator needs about 250.80 volts. So if you're using a half adder to do that, this elevator cannot move on its optimum speed because these units are left out by the half adders. But if you use a full adder to implement the elevator, the full adder is going to put into account the 250 plus 8 volts. So that means that the 258 volts is going to move the elevator up from the ground floor to the last floor with optimum optimum performance. That is why accuracy is more important. Accuracy and precision is more important in in physics and electronics in general. So that is why the full adder is a predecessor, or is an improvement upon the half adder. So this is a combinational circuit that is designed to add the three binary digits. So I think we get the example of what it means when we say that the full adder is more accurate and is more precise compared to a half adder. The full adder is more precise. So if the inputs, okay, the inputs of a full adder. Remember, it adds 3-bit binary number digits or numbers. So it is A, the bit will be A, the second bit B, and also the carry the carry in from a previous full adder. Then it outputs the outputs will be sum again, and then also a carry out. Okay, so that is how a full adder. Those are the inputs and outputs of a full adder. The block diagram of a full adder. The block diagram of a full adder will look like this. So we have a full adder with a bit, takes 3 bits A, takes a second bit B, and then you take also a carry in. I'll draw the carry in from here just to show that it's a carry in, or say C in from a previous adder. Then it has the output of sum and the output of a carry out. So this is a carry coming from a previous adder you're going to put into the calculation. This is a carry out that is coming from the calculation of this full adder. So remember, a full adder is a combination circuit that is designed to add 3-bit binary digits. So it will add a bit A, to add the bit B, and also a carry in. The outputs will be sum and also carry out. So the next video we'll look at the truth table and the logic circuit of